Yes, sir, good afternoon. So today we have Renato Renner who's going to talk about something a bit of the Finetti theorem, I guess.
Right, yes. So, yeah, so indeed, I'm a quantum information theorist, and I will tell you about a quantum information theoretic method, or say some more general ideas in quantum information that I think would be interesting if in the context also of quantum gravity. And let me start by just telling you something that you certainly know well, even if you're not quantum information theorists, namely about what is the operational meaning of von Neumann entropy. By operational meaning in quantum information, we usually mean that there is some protocol or some task that is characterized by the quantity. So in the particular case of von Neumann entropy, one famous, let's say, statement, and this is just one, I mean, entropies have many meanings in quantum information, is that it characterizes the length or the number of qubits we need to encode a certain information. So if we consider system R, and later this may be all Hawking radiation we collect from a black hole, just to give an example where we could apply that. We could ask the question, what would be the minimum number of qubits needed so that we can somehow compress R into these qubits? So this would mean there is some machine which takes as input the R as a quantum system and outputs, let's say, R many qubits. And this is just a way to measure the size of the Hilbert space, of course. And then, again, another machine which just receives these qubits and reproduces a system that is similar to R, so I call it R prime, in such a way that if I would just look at this overall operation, so let's call this compression algorithm or compression procedure. This is a retrieval or recovery procedure, so that this whole diagram is almost identical to an identity on acting on R. So that's basically what information theorists mean when they say we can encode information or we can compress information. But overall, of course, we want to retrieve whatever we compressed, and this is just expressed by saying that this is equal to that. And approximately equal here means the following. In quantum information, these objects are all described as, I mean, this is, every line corresponds to a quantum system. So here's the quantum system containing R, here's the line containing the R qubits, and these things are trace preserving completely positive maps, which is just the most general way to express how we can act on a quantum system. And so the identity is, of course, also a trivial map, and the approximation is just in terms of some norm, which we call the diamond norm, which basically measures, this has again an operational meaning, how well we could distinguish this situation from that. So you could think of like a machine that sees either this or that, but doesn't, I mean, just the action of this and has to decide, and what's the probability by which the machine can actually make, or what's the, you can interpret it as a probability, like what's the probability by which you have an advantage over a random guess what it is. So if you if you can always correctly guess which one it is, you would say the distance is 1. If this look exactly equal, the distance is 0, and in between it's kind of the advantage you have in the guessing probability. So that's just how quantum information theorists think about compression. And now the usual claim is that if you want to know what's the, I mean, now we want to optimize our all compression and recovery procedures such that we achieve this, and we are interested in minimizing the number of qubits here. And then the informal claim, which is not yet a mathematical claim, is to say that if we look at the von Neumann entropy of the state of this system, like we think of a source that produces this, for example, the Hawking radiation, then the R here is basically given by that entropy. So this is what I mean when I say that von Neumann entropy has an operational interpretation. It tells us that we can achieve this. Okay, so that's just a very general thing, and that's not yet complete. Yes.
This is for many copies of R?
Yeah, this is now precisely my next point. So that's so there are indeed two concerns one should have, and you just expressed one of them. Namely, first of all, this is not the correct statement so far because we indeed need to look at something with many copies. The other concern is that it's not so clear what I mean by this von Neumann entropy of R because it refers to a quantum state, so to some density operator. And the question is, what is that density operator? So let me just write down these two concerns, and then I will later refer to them. So let's call it C1 as concern 1. And I will go in the other order. So yes.
So that should be done for all possible R's. So do you have in mind the same two machines for all possible R's that I could fit?
Mm-hmm. That's
or is there
okay.
a restriction of that?
That's precisely now referring to the actually first
It's
concept.
always the same R.
Yes.
Then it's trivial to represent it.
Right, exactly. So indeed, that's so a way to phrase your question is, what do we know about R in a sense? Because if you, for example, knew, let's say, if I'm now these things come out of, let's say, a classical. I mean, if you do classical information theory, one could draw exactly the same picture, of course. And then you could, for example, say, let's suppose R is a source that just produces random bits. And then I could ask, what is now the way to characterize that? And then what I could now ask the question, should this work for all sources of random bits, independently, for example, of the probability distributions there? And then the answer is, of course, different from when I, for example, know that the source always produces a zero anyway, because then I don't need to transmit anything. I just have a decoding operation that outputs many zeros.
But it also depends on how many bits the input is.
Right, it also depends on that. So what I will now, so the first concern that I just wanted to mention is that indeed we need to be clear about what we know about the source. So I call that the source. That's whatever system we, like whatever device or experiment that produces the system R or outputs the system R. And the question, I guess, if I also understand correctly what you mean is, or what you're asking about is, how does this R relate to the encoder? For example, does the encoder, can it depend on the characterization of the source or not? And that's indeed one of the things one needs to clarify. So this is, I could phrase it like this, that I will just write maybe one expression in, but in quantum information, I mean, I need to say one thing that sounds a bit philosophical, but it's actually very relevant technically in quantum information, namely what is the interpretation of a density operator? And of course, this refers to how do we interpret wave functions and goes into a philosophical debate. But one important point, because in quantum information, we want to talk about the information we have about something. For example, if I'm tossing a coin and there was this outcome which I didn't see so far, then I associate to that coin, to the outcome, a completely mixed state between heads and tails. But of course, someone who has seen the outcome of the coin toss would say, no, the state is, for example, just heads. So two agents or two different, I mean, in quantum information, we talk about agents. Two agents with different information about the experiment would assign a different state to the outcome of the coin, just reflecting the fact that they have different information about it. So that's something to keep in mind. And in quantum information, the way we sometimes write this down is we say we have this notion of conditional entropies. And so I still use the von Neumann entropy and will now not yet provide a definition, but it's just so far on the intuitive level, could say, we have this conditional entropy, and let's suppose A is the information that some agent A has. And then what we are really interested in, what is relevant in quantum information to characterize tasks, is how uncertain does R look like conditioned on the information in A. Maybe I should still just, for completeness, write down the definition, which is if you look at the situation basically from the outside, we could associate the joint state to the, let's say, coin or whatever it is, and the information that someone holds. And I mean, that's just a technical definition, this difference of Neumann entropies, but the idea or the interpretation is this is really the uncertainty A has about R. And the point is that generally, this is of course different for different agents. So if you have another agent B, you may associate or assign a different entropy to the same system. So that's an important point, that the entropy is in a sense not a property of the system we are looking at, but equally well or even more a property of like from whose perspective we are considering a system. And the example of the coin just illustrates that, like someone who hasn't seen the outcome of a coin toss would associate 1 to this measure, and let's say B is Bob who has seen the outcome, we would say 0. So that's so one concern is that we have this fact that they are not equal, and now the question is which one is the relevant for this thing, for this scenario. So we need to ask what if you have two observers, and of course it's somehow related to what do we know at the point where we design this compression scheme and the recovery scheme. So the answer will have to do with the idea that it has to be, we have to measure the entropy, the uncertainty relative to the whatever agent or person who designs this compression procedure. So it's in that sense, there's a dependency on what you know about the source that we can capture. I hope that's good as a preliminary answer to the question, but we'll come back to that. So far, it's just a concern that we have this problem that we need to solve. And the second concern is exactly what you said, that usually in quantum information, we talk about repetition. So what is actually meant, and I will change this slightly and correct it in a sense, is that we assume we have n copies of a source. So we need to somehow think of a system that we can produce many times, let's say n times. And then we send here R times n many qubits forward. And here we get, of course, also n copies of this. And we want that this corresponds to, if this is the identity on R, we want that we can, so we basically want to transmit R copies of the system.
But you don't actually get n copies if you want. That's something which is hopefully close to n copies.
Right, so that would just be this, right, so this would just be the space has this form, and indeed, and what it means that we have that is, what it means it's really very close to that channel, that's right. And now, of course, this is just the space, so we have to ask ourselves, what's actually the state on that space? And the usual assumption this is just a standard assumption in quantum information, which is one thing I will question, this will be basically the main topic of this talk, is that the source produces a quantum state of the form rho tensor n. So we usually assume in quantum information that we have scenarios where some process is repeated many times. And of course, then the definition of R is somehow in the limit. So we are asking what's the minimum R such that this can be achieved for large enough, for a large n. And so what you're assuming is this independent repetition of a process. So this is called IID for identically and independently distributed. That is, of course, a well-known expression. And one could say all of, let's say, 95% of work in classical information theory, as well as in quantum information theory, somewhere introduces this assumption. So whenever you see a result about coding, channel capacities, or whatever, usually this assumption comes in somewhere. So that's important. Now,
so I have a question probably
yes.
related to what
Yes.
he was asking.
Mm-hmm.
In the way I like to think about this, you can take rho R and then you can purify it with some reference system.
Yes. Mm-hmm.
And then are you demanding that the second line preserves that entanglement? Because
Yes.
if not, then I can just throw, I don't need, and you know, R can be, little r can be 0, right? I
Yes.
just make a bunch of copies.
Yes,
and-
right. Yeah, that's a very good point. Actually, there are two equivalent ways to say the same thing, and this is one way, and what you have in mind is another equivalent way. Because what I'm saying here is that I regard this picture here as a quantum channel. So this whole thing is a map.
Yeah.
So I, for a moment, disregard this rho n and just say, this map from here to here is close to the identity. And that, of course, doesn't allow you now to reproduce something which is unrelated to the input, because then it's not the identity map.
Yeah.
Now, an equivalent way to say the same is to use what we call in quantum information the Joy-Minkowski representation. So we just say, let's not consider this as a map, but let's assume we have here an input, which as a marginal, let's say, has, for example, this distribution, but it's actually entangled with some reference system. And then we are only looking at the map that, or the state that comes out. So what we are doing is that we have here some entangled state with some reference.
Yeah.
I will now not use R for the reference,
Yeah.
but then I look at the joint state of this.
Yes.
And this joint state is a full is actually an equivalent way to characterize the channel from here to here. So a different way to express this, although one has to be careful about the norm here, in fact, is that the state, the joint state of the reference and the channel output is equal to the joint state I would have here. But here it's just a trivial state, because here, if I have a reference and there's an identity, just the same entangled state arrives. That's probably why. So.
Yeah, but it seems either way of thinking about it, the protocol has to refer to other states besides just the one whose entropy you want to compute, right?
Aha, yes, now, okay, yes. So these are the two different ways. Now, if what we want is that, so whenever I'm now comparing these two channels, so if I'm comparing channels, I still need to say somewhere what's the input distribution to the channel. So actually, in the case that I had before without the reference, if I say this scenario is close to that, and I say this is epsilon close, this epsilon refers to the probability that I have a deviation when the input statistics corresponds to that. In the case of the Joy-Minkowski representation, actually this entangled state that I choose is not the maximally entangled state. It's just a purification of that. And then they are equivalent to two things. But in either, as you correctly say, in both cases, it depends on that choice. And that's important, because if I didn't make a choice here, then it has to work for whatever the input is, and then trivially, this R is just equal to the dimension of, or log the dimension of R. Is that what?
Yes.
Yes. So basically, just to summarize so far, it's important to make this problem non-trivial or even interesting, one has to specify what is the input distribution, but the question is basically what is it? And the second point is, as I said, we have to somehow assume anyway repeated processes. So I call this here IID, and we need to justify this. Okay, so this was just a kind of slow introduction. Let me now turn to information theory, or to, let's say, how information theories deal with that. So the first thing to say is that information theories just assume IID usually from the start. They don't further justify that. And it's okay, because in most applications, they are talking about things which, to good approximation, are just repetition. So what do information theories do? They look at communication over a noisy channel. And each time I send a bit over a channel, you can assume, if you are generous enough, that the noise model or the noise that affects the bit is kind of the same. And maybe there's some small short-term correlations, but basically there's nothing bad happening if you assume that each time I invoke the communication channel, it behaves in the identical way. And even if the assumption is not correct, at the end you do an experiment and actually transmit information, and if it works, then you can say this was a good assumption. So that's why most of the tools in quantum information, in classical information, therefore also in quantum information, which is based on classical information theory, have been based on that assumption. Now, I think what is important to realize is that this assumption is a highly non-trivial assumption. So if we now are applying QIT tools in setups where it's not clear that we even have a repetition of a process, or in scenarios where we have repetitions, but there's no good argument to say that the individual repetitions are independent, we need to be very careful, and we have to ask, do the usual tools, the usual statements in quantum information still apply? Now, this question is an old question, and the first one who wrote about this question, as far as I know, was a classical probability theorist. He did that before we had information theory, but similar problems arise already in classical probability, and this was Finetti. And so the theorem I will later talk about is, of course, by Bruno De Finetti. He's an Italian mathematician, and he developed ideas in the 30s in classical probability theory to deal with this concept. But just to emphasize that he already realized how important that is, he wrote a paper on the foundations of probability theory, and the paper starts with a chapter which has a list of warnings. So the 6 warnings. And it's kind of interesting. I just read one of them because it's hard to remember the exact wording. But what he wrote is, so there are 4 warnings which are of different nature, some misunderstandings people have about probabilities. And then the 5th and the 6th warning. So the 5th is that the concept of stochastical independence, he means that, has absolutely no objective value or meaning. So he was already concerned about that. And then his 6th warning is somehow almost identical. He says that the most common and misleading error made is that we consider an identical and independent repetition of processes. And he says there is really no reason, in particular, if you look at scenarios, or he says, if you use that assumption, we should never use this assumption as a starting point for a general theory. I mean, I don't want to use this citation as a justification for what I'm doing, just making clear that this concern is already 100 years old, that this idea assumption is not a good assumption a priori. It's only in special cases. But De Finetti was then, of course, worried about the fact that many probability theoretic statements already assume that, and his goal was to somehow justify that, not by just, let's say, looking at the physics of the process, but in a more mathematical way. And this idea he came up with is to use other assumptions which are more operational. They're symmetry assumptions from which something that is close to this ID structure can be derived. And that's the, let's say, underlying idea and motivation for what I call the De Finetti theorem. So we'll now state that theorem, and then we can return to these concerns and see how they would resolve these concerns. And I think the reason why I'm talking here in this audience about the De Finetti theorem is that I don't know how serious this is usually taken, but when one reads papers about Hawking radiation and entropy, sometimes people make this relation and say, actually, it means that we could encode the Hawking radiation in this many qubits. And I think it's important to understand what that means and what the assumptions are, because it leads sometimes to different conclusions. And just as to give that rough idea already is that if we, for example, ask this question again and drop this assumption, then it's no longer true that this relation here holds in check. So it's really, in a sense, necessary. I mean, it's not, I would say generically, it's just not true. So on the most conditions, it's something else. And we will see what it is. Okay, this was a long introduction. I will come to the slightly more technical part, but I will keep it, or I will start with a picture. So what I'm going to do now is to phrase what in quantum information theory is called the quantum De Finetti theorem. And it's almost identical to De Finetti's original result, except that everything applies to the quantum case. However, an important aspect actually of this quantum result is that it's not possible to derive the quantum De Finetti theorem from the classical one. So it's a generally new theorem. And one can make this statement even stronger by saying that if certain properties of quantum theory were slightly different, then it wouldn't hold. And there are other indications. For example, as a let's say preliminary thing that is maybe good to keep in mind, classically, the De Finetti theorem holds independently of the dimension of the subsystem. So, for example, if I didn't have a bound on this R, I could still apply on the dimension of R, I could still apply it. In quantum information theory, there are counterexamples. So it's important to have bounds on the dimensions of the involved Hilbert spaces. So that already shows that there are some qualitative differences. Okay, but are there questions so far about the motivation? Otherwise, we'll proceed now with the De Finetti statement. Okay, then, okay, so the definitive statement is the following. So we look at draw it like that. So we assume we have just a bunch of subs. So we have a n-partite system, and I call the subsystems R with an index, which tells me which subsystem it is. I assume there are, let's say, I number them somehow, Rn n plus 1, and the last one is called Rn. So this is, the assumption is each of these subsystems has the same finite dimension. Now I will also assume there may be, this is just a way to represent the system with many subsystems, there's some other subsystem E, which is just anything else we may have. Now, in general, a quantum state on all these systems is I would denote it like this, is a quantum state in R1 and R capital N. So capital N is just the total number and E. And let me first make two definitions. We say that this state is permutation symmetric, and this definition is pretty obvious, but it's what is maybe relevant or not completely standard is we say it's permutation symmetric with respect to E. So we have to specify that there is, so this just emphasizes we are not only talking about these R systems, but about some other system that again serves kind of as a reference, if you like.
So what does that mean? What is E? How is E?
Yeah, so E is appearing just the system. And now what it means is that if for all permutations pi, so let's say pi some permutation in the permutation group on n systems, if I apply pi to that quantum state, so pi just acts on these n systems and leaves E invariant. So I could also write pi tensor identity on E. Then it should be the same state as I had before. Now note that if I didn't have the system E, this would be a much weaker statement, because if I include E, it means that I keep all the correlations with E intact. So that's, I don't know whether this already answers your question, what it means with respect to. So permutation invariance with respect to E is a strictly stronger statement than just permutation invariance of the marginal state.
So which states are permutation invariant in N and cannot be extended to having an E?
So you can always, so if you start with something that is just without E, you can always tensor it with some independent system E. So it's more like if you're given some state which already has an E, this is not a non-trivial condition.
Does any permutation invariant state without the E have a purification, which is permutation invariant in this sense?
Yes. Yes.
Yes.
Yes. So it's not a difficulty if I give you that state and it's permutation invariant. It's trivial to construct one with an E. I just take a tensor product with some. But
that's the only way to construct.
Not necessarily. Actually, a different way is it can do something like a. Okay. Let's suppose let's even take a classical example. So a classical example could be you take the let's say you have R are just each system R is just one random bit. That's an example. And now you could say the state of n bits could be defined as the state which consists of all bit strings of length n, which have exactly, let's say, 100 zeros in it, and the rest are ones. So that's a permutation invariant state. Now you could have the mixture of such a state with another state, which says there are 200 ones, and the rest are zeros. Now, if it's such a mixture of two symmetric states, I could put into the E the information about which component in the mixture it is. So then it's not a product, but it still satisfies the condition. So it's not the only way. So there are interesting, let's say, states which are of that form. That is actually irrelevant.
There's sums of products, right?
Yes, in that case, there would be sums of
But
products.
I think that's the most general. Because.
Yes, so you could, in principle, even have something which, if you consider E as well, so you could do what I said, but in a superposition, and that would still work. I think you have to take into account superpositions as well. Okay, so that's one definition. The other definition is that I call a state R1, Rn to have the Finetti property. So I just call it Finetti. That's the usual expression today. With respect to E. And that's now less, okay, the definition is very natural, but it tries a bit more space, effectively. If the following holds, if I can write it in the following form, and these are actually the ones that look a bit like convex combinations. So if I can write it as a sum over some W from some finite set, so that's important, this is some finite set, and the state is of the form some sigma R, so that's on, when I write R, it's just one system of the type of all these systems because they have the same dimension, so they're all isomorphic. And this sigma depends on the W and is repeated n times. Tensor something else, some state theta on E, which also depends on the W. And some weight, maybe I put the weight here. So I put some P W here. Where, okay, maybe I should say it. So the P W is just some weight. So it's a positive number or zero, I can put it like this, some non-negative real number. And sigma R W is just a density operator on R, and the theta E W is a density operator on E. So that's what I call a Finetti state. So basically, if I forget this E system, a Finetti state is a convex combination of IID states. And with the W, it's something which is also a convex combination, but in the E state, it factorizes from the E states. So these are actually very nicely behaved states. And now what the Finetti theorem does, it relates these states to those in the following way. Just erase this. No.
So W is a finite set.
W is a finite set, yes. Right.
Does this grow?
This is just
Does it
useful.
grow as n?
Fun.
Can I allow the W grow as n? Some function of n?
Capital.
Yes,
Capital N.
yes, yes. It will check. So in the theorem, I will, okay, one could even give bounds on it. In the theorem, I will just state that there is some finite. Okay, we'll just see. Right now. So quantum definition
Is it important that's finite because it's a more restricted class, or because you can always do this finite?
So it's just useful. So the theorem is stronger because it will say any, so what does the theorem say? It will say if a state is permutation invariant, then if I trace out some subsystems, it will be close to a state of that form. And of course, this is a more restricted class. Now for technical reasons, if I want to work with these states later, it's of course useful if I know that I only need to have a finite combination, then I don't need norms and so on that space. So it's just, let's say, technically useful, and it's easily, if you look into proofs of quantum determinism, it just comes out more or less automatically. I mean, yeah, one has to work a little bit, but compared to the infinite person. Now I should say that, okay, even though I stated like that, there are several variants of the theorem, but the variants just distinguish themselves by like having bounds which are more or less tight in different regimes. And I will just give one of them so that you get the idea. And depending on the application, if it's really about, let's say, optimizing something in terms of parameters, one may do different things. So it says that if, or for any, or I just put it like, so I consider such a state, which is permutation symmetry. And then the statement is that there exists, or yeah, so the n is fixed. Then there exists a Finetti state, which I will call rho bar R1 until Rn and E. Actually, if I want this state also to be symmetric, I would need to here trace out a little bit and only take n half, but that's not relevant for the moment. So that's a state that has the Finetti form. With respect to E, such that the following holds. And now, it's true that for all n, and then any natural number, actually, it's only useful if this number is smaller than capital N. The reduced state. So if I only write here R1 until R small n, I just mean that I trace out capital N minus small n many systems, is close, so there's a norm, to this Finetti state, the one with the bar, in the one norm. So that's the usually operationally relevant norm, because again, it has this property of being distinguishable with the corresponding probability. And now it tells us something about this norm. So there's some constant. Constant is actually approximately 10, so it's just a number. And then it's the dimension of R. As I said, this is a difference, by the way, to the classical theorems. And then here we have n divided by capital N. So that's the statement. So it says that in the regime where we only consider, let's say, here it's up to n, so the number of systems we are interested in is somehow sufficiently smaller than the total number of systems that there exist or that I've produced in a symmetric way, then I can say that these systems are in this convex combination of IID states. So that's the claim. Okay. So you see, this claim will be important because it reduces the assumption of IID to a symmetry assumption, but it's not really the ID, it's this. So this convex combination is actually important. So this is not the same as an IID state, it's a convex combination of IID states. Yes.
So how tight is this in the sense that can you find examples where you saturate?
Yes, more or less. I mean, yes, that's a good question. So the tightness has been studied quite well. And so in this, so the square root is not necessarily tight here, but otherwise the scaling is tight. So you cannot expect to get something good if the ratio between small n and large n is not small. And also the dimension is necessary. And there's an interesting counter example. Actually, there is a very nice paper by Matthias Christandl and Andreas Winter, where they show that the totally antisymmetric state, which is a permutation invariant state. So the antisymmetry just refers to you have a pure state, which as a pure state is has a sign when you permute, but as a density operated symmetry, this state maximally violates this. But the totally antisymmetric state needs the dimension of the subsystems which is equal to n. And so, you see, of course, if I have here also an n, then the whole thing doesn't give me a bound. So in that sense, it's, let's say, if you're not asking about concrete, let's say, constants, this is more or less tight. How? Yes.
Maybe you already said this, but can you give us an example of a permutation invariant state that is not definite?
Yes. For example, the so-called G. I mean, I didn't say it so far, so maybe I should have done this. And the so-called, okay, I can even give one without an E. And an example is the so-called GHZ state, which is just a superposition between all zeros and all ones. Also, a state that is not definite, which is just the same, like even classically, this has not such a large deviation from it, but it's the state where I take, again, classical bits. So each of these is a classical bit, and I just take a bit string which has exactly equally many zeros and ones, and I randomly permute them. Now, because an ID state has some fluctuations in the number of zeros and ones, it has actually a large distance from a state which has exactly equally many zeros and ones. So a state with a fixed, let's say, the frequency of symbols that occur classically is also an example of a state which cannot be written like that. This is maybe a less interesting example, but the GHZ state shows that there could even be entangled states, whereas what the Finetti theorem tells us is that the entanglement gets completely erased from it. So this is actually important, because what makes proofs a priori, let's say, difficult would be if there was long-range entanglement in these states. So, and of course I can have a symmetric state with long-range entanglement like the GHZ state. And so I'm not sure GHZ state is special. Okay, it's just this the auto-normalization. So this has, in a sense, very long-range entanglement.
Here, once you trace out the
Here, it's an extreme case, because here I would only need to trace out one. But now I can, of course, write more complicated stuff, which doesn't have this problem. So if you only had such states, the Finetti theorem would be highly suboptimal, because then, of course, you see, I would only. But this is maybe a misleading example in that sense, because usually it's really necessary to trace out many split codes. So it's maybe just, this is maybe, okay, a good point to just very briefly say where this comes from. Actually, the area in which these things were developed is quantum cryptography. And the reason why it was developed there is that quantum cryptography is precisely an area of research where you want to apply quantum information theory tools, but you basically don't have an IID assumption. Because in quantum cryptography, you deal with an adversary. So there's, for example, you have communication between Alice and Bob in n rounds, but in each round, an adversary could do arbitrarily complicated stuff. It could take out the qubit that I sent and insert it in later rounds. So in quantum cryptography, we are dealing with n-partite systems which are a priori in an enormously complicated state. And this is the reason why quantum cryptographic security proofs are extremely hard to do. I just have to look at Barbara, because when we were both young, we had a paper together on a security proof, and already at that time, this was the time before the Finetti theorems existed, and we somehow used some symmetries to get rid of the problems. But the problem is really a priori you have some arbitrarily entangled states. Now in quantum cryptography, therefore, you still want to deal with entropies and so on, and you need an operational meaning, because they really need to know how much can you compress stuff. So the big question in quantum cryptography, how can we reestablish the operational meaning of the entropy so that we can actually apply the tools? And the Finetti theorem was basically the key to that, because it reduces the arbitrarily complicated state to those, provided we have a symmetry assumption. And this is now the other important point. What's so different about the symmetry assumption and an ID assumption? You could say this is just another assumption. The crucial difference is that the symmetry assumption can be enforced usually. So again, just give the example of quantum cryptography. The way one deals with this is just one says, if let's say we have a scenario like this, Alice and Bob communicate, they use now n times the channel. Maybe I could depict this like this. So we have n uses of a channel. Now, if after using this channel n times, Alice and Bob could locally apply a random permutation to the order, and the same random permutation, but then forget how they're permuted. This is like an averaging over all permutations. So the state you have after you communicated with an arbiter. So here an adversary could introduce arbitrary correlations, which are not symmetric at all. But at the end, you randomly permute everything, which can be done locally. So a random permutation is something you can do locally if you do the same at the sender and receiver side. So you can actually turn by an explicit mechanism any state into a permutation invariant state. Of course, this is incredibly expensive to do, but sorry.
No, go ahead.
Yeah, so this is incredibly expensive to do because to apply a random permutation, which is the same for Alice Pop, you have to communicate what permutation you apply. Now, the nice thing in the case of quantum cryptography is that you just do that in the security proof. In the security proof, you assume in a protocol, we just construct an artificial protocol where you do that, and then one has a separate proof step where one says, actually, this random permutation didn't change anything in the final statement. So one introduces it and then proves everything under this nice permutation symmetry assumption, and then has a separate step which says this permutation was actually not relevant for the final state. Any statement that holds without permutation symmetry also holds with. So, okay, that's just as a remark how this is applied.
Sorry, so this is exact permutation symmetry.
Yes,
right?
it's
Not
exact
approximate,
permutation symmetry. That's
yeah.
important.
That doesn't seem like a particularly more realistic assumption, right? Like if I'm a submarine captain and I have to send a message to headquarters each day, the days aren't permutation
Yes,
and symmetric.
precisely. That's indeed why I said in quantum cryptography, if you needed to do after all this random permutation, it would be extremely unpractical.
Yeah.
However, and the reason why it worked, so at the end, as I said, you can say, even though we now looked at a scenario where you hypothetically have this, we can equal it to the other one, is that if the protocol that you're using is itself permutation invariant, then it doesn't matter. So if everything so normally in QKE protocols, you don't actually treat so the receiver doesn't treat the individual signals differently. This is not a priori the case for all protocols, but in usual communication protocols are permutation symmetric, and then you can do that again. The other way to see it, like in physical contexts, let's say Finetti derived all this, I mean, he didn't derive the quantum version, but his motivation was the following. Let's suppose we do a physical experiment. In that case, it was a purely classical experiment that we repeat n times. Like today, we could say at CERN, there are n particle collisions. Now, how can we really be sure that if we analyze these particle collisions, they were independent from each other? Of course, intuitively would say they are, but how he was concerned with the question, how could we actually really make a firm statement they're independent? Now, he would say that if we analyze all the particle collisions, what we are doing is at the end, at the very end, we just look at statistics, we look at counts. And of course, if we count stuff, then this is invariant under permutations. So it's somehow the analysis we do on the data is covariant under random permutations. So we could as well do as if at CERN we did all the collisions and then randomly permuted the order before we analyzed them. And then we again have the permutation invariance, and then this applies. So this was the argument how he said that if you do a physical experiment, what we should do is just in our data analysis, make sure that we don't exploit any order, which we usually don't. Like if I do an experiment, I measure the mass of some, let's say I wouldn't know the mass of an electron, I would now randomly produce or find or.
I think you're saying you're projecting onto the symmetric part of the state.
That would be the mathematical way.
Yeah, but
to do
that
it
might...
if you were in the, let's say, so this is not a pure state.
Yeah.
So if you had the purification, you could do that.
Yeah. But then it might not be the dominant part of the state or something, right?
Right.
Lose information.
Exactly, but it's actually not the so I think there's a huge difference between, in a sense, projecting, which would involve a post-selection and indeed doing a random permutation as a so doing the random permutation would involve really generating a lot of randomness and then randomly permuting it. But the point is that even if you do this in an argument hypothetically, at the end it's usually a separate step to say this was actually not needed, because anyway your final statement that you're making, let's say at the end you make some claim like that from the data you discovered the Higgs boson. Then you can say this statement was actually invariant under if you permuted the data initially, and therefore we could for the analysis, assume it was randomly pending. So yeah, I think it's actually at the end not it's a very easy to realize assumptions whenever we have setups which are themselves already permutation invariant. But if the task that you're carrying out is permutation invariant, then we can always assume that this is.
It's very different from projecting on a symmetric subspace.
It's very
If you
different.
were
Yes.
projecting a
Yes.
symmetric subspace, you would
Yeah, you
multiply
use
on the
most
left
of this.
with a permutation average, whereas here you conjugate with a permutation.
So it's really not the same. I mean, of course, the result is you get a permutation invariant state, but it's not this. Yeah, that's something very different.
But you could get a vector in the antisymmetric space that would also be a permutation invariant.
Yes. But would not be useful because then, as you said, you would lose most of the stuff. So you really want to do a random permutation. So operationally, that's a very different thing. If I then having a
The
machine.
pure state in the antisymmetric space is symmetric under that definition,
Yes,
right? So
yes, exactly. But yes.
I mean, I think we could have, I mean, if some adversary was messing with the LHC collisions in some correlated way, like they could totally trick us into thinking we saw the Higgs when we didn't, right?
Yeah, I mean, I didn't now claim that there is no
Yeah.
a way to trick us, but actually at the CERN, but in quantum cryptography, you're precisely doing that, what you're saying. So in quantum cryptography, the big challenge is to say that let's derive a statement, in that case, that some key is secure, which actually involves other intermediate statements. For example, in quantum cryptography, you need to do some state tomography. Yeah. But the state tomography needs to be absolutely robust under any adversarial influences. So indeed, if you do this, if at CERN we did apply the quantum state tomography procedures developed in quantum cryptography, then we could say nature couldn't trick us, because in cryptography, really paranoid. We just assume anything can happen that is not explicitly excluded. And so I would say there are, in principle, schemes to achieve that. Of course, they're not applied in the context of CERN, but that's precisely what we do in quantum cryptography. We have schemes which are working under absolutely paranoid assumptions of what's going on. So that was just a small to say where this was developed. There's, by the way, a problem in cryptography with this thing, because in cryptography you want, of course, if you think there that these are the communication rounds up to here, and then the theorem tells you, oh, you can only use those because only for those we know their IID. It would be very unpractical again, because it would mean the rate at which you can generate key is extremely small. So we can only make a state that only can say this state is nice, this part of this many systems are nicely behaved, but all the others which you also have to communicate are lost. Now, the way to resolve that is just, as I said, there are different versions of the Finetti theorem. There's actually a Finetti theorem, which instead of this bound has a much stronger bound, which, okay, now it seems I'm contradicting what I'm saying before, but there's a resolution. The bound says you only need to trace out a small fraction of the systems here, an arbitrarily small fraction, and you even get an exponentially small difference here. The catch here, why this is still correct, is you have to slightly weaken the definition of what you call a Finetti state. And the weakening you have to apply is called an almost Finetti state. And basically what you do is, it's the same definition, except that you allow that a sublinear small amount of systems here are in an arbitrary state. So it's basically like, if you assume, if you allow a few errors here, then you can get a much, much better Finetti theorem, which is called the exponential Finetti theorem. This is the one that is used in practice, so to speak, in cryptographic security proofs are based on this exponential one. Then it allows you to use this whole key, and these few errors don't matter because the things are robust there. So this is just the same.
Exponentially in the size of the error.
It's actually the bound is of the form E. So let me maybe it's okay. It's exponential in, and then there is something like, okay, I will not write the dimension dependence, but it's number of errors times n divided by n. Up to okay, there's a constant here. So in other words, if, for example, you only, sorry, So
Yeah, it should be.
this is n minus, this is now n minus n. So this is the number you trace out. So this means that if you only trace out, let's say roughly a square root n, which is very small, of course, and you allow a square root capital N many errors, then you are in the regime where this exponential kicks in and makes things arbitrarily small. And you see, this is very, so this goes to zero very fast. Is this what you were designing? Yeah. So there's really a huge, so allowing errors here makes a huge difference, but that's now not the point for this. But that's actually good. Otherwise it would be completely useless in practical situations if you didn't have that. But okay. And
So,
maybe,
so
yes.
this theorem, like you fix the W and it holds for all the N, right? For all the little.
Yeah, so we fix, right. So this is actually a version I should mention. So this is not the version that is usually stated. It's a slightly changed version that I actually developed together with Jinsao Wang, my former student who was also here last week. You know him. And so there the order of the quantifiers is different. So usually you say for all n, there is a state of that form. So here we have reversed it. There's really one Finetti state, and then this statement holds for all n. It's a slight
so the W
improvement.
choice depends on little n.
The W only depends on, so the sum here only depends on that state here.
Oh, okay.
Yes.
Okay.
And
It's
not
fixed
on the small
and
n.
for little,
Yes.
for all.
Yes, right. That's the point. That's somehow useful if you want to make statements which we wanted, where you change this n, because you don't want to change the state. Okay. Now, the next thing, okay, that's the Finetti statement. Maybe the last historical remark is that the Finetti's original statement, first of all, was not asymptotic, so it was just basically for capital N being infinitely large, but it wasn't quantitative. And there was later an improvement of the classical version of this theorem, where, of course, the density operator is just a generalization of a probability distribution. So if you imagine there are probability distributions, then you can write down everything in the same way. But then you can get an improvement where this dimension R is replaced by another factor square root of n. And then this means that if n is sufficient, if the small n is sufficiently small, independently of the dimension, you get definitely close to a definite state. This is just as remarkable. And as I said, the antisymmetric state is a counterexample to that in the quantum case. So there is a huge qualitative difference. Okay, now in the last part, is there still, I don't know how much time. Okay, so this is the review of the theorem. Now the question is, why is this useful, or what do we do with that? And the first thing to be said is the following. Now makes information theoretic statements which hold only under the symmetry assumption, or if I replace the ID assumption by the symmetry assumption. And for example, the statement we had before, like what is here in the box, can be now generalized, or can be adapted, I should say, to the situation where we have general quantum states. So what I mean by that is following. Let's again take this scenario here. Now I get rid of this ID assumption. I just assume I have here some arbitrary state. Here I don't even need the E system, by the way. So the E system is here trivial. I have here a state of n systems. And okay, now I used here a small n. Actually, to make the connection now to what I said before, let's use this capital N, because I really mean everything. Now, what I'm doing, so if R1 until Rn is symmetric, if that's the assumption, then we can show that the rate, so this R is really defined by the minimum amount of qubits per R that I want to transmit, is given by a quantity, which is, however, not the von Neumann entropy, but it's something we call the regularized von Neumann entropy of R. And of course, this regularized entropy depends actually on, of course, on everything, because I now need the information how things are correlated. So how is this defined? So the claim is that one. Maybe like this. So this is defined by, it's just an asymptotic definition. I use here a different n, small n. That's just because okay, you see, in order to do that, I need a class of states. I cannot define it for one state. So, or I could make this quantitative and then just say n has to be sufficiently large. So I look at all these systems and I look at and this is the von Neumann entropy. So I can define a new entropy measure. This is a general procedure. We can regularize quantities. And regularization in quantum information, we usually mean this, that we just take the quantity and evaluate it for n subsystems and then divide again by n and look at everything in the limits where n is very large. Now, this is generally not equal to the von Neumann entropy of one subsystem. Say, look at the first subsystem. That's, of course, not the same. However, this is now an example where we could really say the rate form or the compression formula. If you ask what's the amount of information we can compress it to, is not given by the von Neumann entropy, but by the regularized entropy. So if someone calculates the von Neumann entropy and said, now actually this tells us how well we can compress information, this is only true, I mean, or you need some additional assumption, for example, the ID assumption for that. And if you don't have the ID assumption, then you don't get that. Here, this means under the weaker, generally weaker symmetry assumption, or the easier to justify symmetry assumption, we have this. So that's the thing that, so what does this tell us? This tells us some statements in quantum information theory, like this compression statement, which is a very basic statement in quantum information, are still true, even if you don't have the ID assumption. They're true for the symmetry assumption, but they look different. They're actually different expressions, which of course, in the special case of ID, in the ID case, the regularized entropy is of course identical to the von Neumann entropy. I go back to that. Yes.
You didn't assume that the state was definite?
No, here, in the proof of this statement, one would invoke the Finetti theorem.
So you do assume it's definite. So you
No,
do
it's
assume.
No,
symmetric, and then you use the theorem
yes.
to tell
So
you it.
actually, there's a non-trivial fact here. So if this is symmetric, it's not true that the total state is symmetric, only a small part of it. And so definite. So if the whole, let's say I have this picture with n. So what I'm assuming is that this total state here up to Rn is symmetric. What the Finetti theorem tells me is only that if I look at a small part where I go only up to n, that this is approximately definite. That's what the Finetti tells me. So let's say that so in order to prove that statement, one actually makes two steps. One first proves it for Finetti states. Then one shows it's robust under this approximation, which is a standard argument, because entropy is robust under small changes. And then the non-trivial step is to say that even though I now only talked about this small part here, I can still generalize it and say the total state, I can still compress it or apply the result to the total state. So it's a combination of.
I'm confused about the following. If you have a definite state, it's clear you can have one that is capital N goes to infinity.
Yes.
But if you weren't given a priori that the state was definite, I don't understand what kind of sequence of states where capital N can go to infinity. Give good examples of this.
Oh, so typically, okay, maybe, so a sequence of states is, for example, the sequence of GHZ states. And
Yes.
but usually, okay, I mean, this is one way to think of it. In practice, one usually thinks so, but this is just a way to state. So all these bounds can be made finite. So I can always say, writing this limit is just an abbreviation for saying that for any finite n, I know precisely how well this is approximate. So in practice, I don't need a sequence, but if I wanted, I could look at the sequence of, for example, GH states.
Sorry, Henry, to take little n to infinity, you surely also have to take big N to infinity.
Yes.
Right.
That was what I was asking.
Yeah, I'm saying what Edward was saying.
Yes.
So then, and then just saying you have a sequence of symmetric states as big N goes to infinity is clearly not enough. There needs to be
Yes.
some sort of
Yes.
regularity.
Yes, you're absolutely right. So that's,
I'm just
like,
saying
if
what
I
you're saying.
state it like this, I should just say, let's make this quantitative and stop, or like, just, okay, I mean,
There's an order of
let's say,
lines.
what I can write down a more fine-grained statement here and say that this is, of course, it's no longer a definition, but what I can say is that this is this plus something of the order, and then it's actually decreasing with 1 over n. So something like this. So I can make these statements for finite n. I don't need to look at the sequence. So in particular, I can look at them for an n which is smaller than capital N. Actually, we'll come back to that in an application.
The confusion is the state R1 to R small n still symmetric with respect to all subsystems big N?
Yes, so this should be,
That's the
yes,
confusion.
so right,
Yeah.
so the okay, yes. So the confusion, okay, this is really maybe unfortunate that I had that, because this is given, and now I look at, so in principle, I usually have something where I have a sequence where I can make this larger and larger. Now, if I state it like that, the more careful way to do it would be to say that I have, if I want to, so the question is, what if this n is fixed? Then what I do, I just look at the version where I take this n only to something which is close to capital N.
But the simple O of 1 over little n doesn't make sense unless big N also can.
This one.
Yeah, that
or
doesn't
one,
make sense.
Yes.
if Capital N is finite.
Yes. So yeah, because okay, if n is smaller than this n, I still get a bound. Yes. But let me, okay, here was, I will have an example where this will become clear. This was just, okay, I will have, so let's return to that question in an example which actually shows precisely that point more.
Yeah, so here, yeah, because you didn't specify, maybe you explain later, so like, do you assume a hierarchy of capital and little n? Like, so
Yes.
why not just simply
Right.
say
Yes.
little n
Yes.
equal to capital n, take capital n
Yes.
to infinity?
Yes.
Does that still work?
So, okay,
No,
let's put, so
Right.
the way I phrased it here,
I say
actually,
no.
this part,
no, because to do D Finetti, little n needs to be small. compared
yes.
to capital.
Oh, yeah.
For the
yeah.
Finetti,
Yeah.
right, for the Finetti, I have this thing needs to be small. However, in order to do, so that statement, so the way you should understand this statement is really I have families of states somehow, and I make this statement. I have some given family which I can use for any
My
capital
question was,
N.
what are good families? So
Mhm.
Finetti would
Yes.
give us a good family.
Right,
But what is,
yes, what,
if you're
I
not
will,
talking about that, what
I
is
will
a
have
good
an
family?
example.
Well, you can't tell us the definition of a good family? I was
Ah,
hoping.
a good family, okay, a good family will be given by the application. So for example, if you have let's say, if I apply this, let me first give a cryptographic example and then quantum gravity type. So in a cryptographic example, we have, usually we look at protocols with n rounds of communication. And in order to define, then we leave that as a parameter. So each, like when we start the protocol, the quantum communication protocol, we fix the n, and also, let's say, if even in a quantum cryptographic thing for the adversary also knows how many rounds. And so the family is just given by whatever the protocol produces for that n. So for each n, it's defined what comes out by the protocol. The protocol is something finite, so the protocol will run and has some, it's like a program that has as a parameter n. And so the family is defined by whatever that program produces. So that's in the quantum, so in other words, in quantum information, I have an algorithm which takes as input n and produces such a state. And then this automatically gives me a family.
So you're saying any algorithm that produces symmetric density matrices like capital N copies
Yes.
for every n.
Yes, and then I need to have, of course, what I then require is that this thing has to come. So in general, this could be very different for any n. So the statement is if this regularized entropy actually exists, so if this limit exists, then I can make this claim that the rate corresponds to this.
You don't ask that the reduced density matrix on the first little end.
Doesn't need to
has a
be,
limit?
no,
Only the
the
entropy?
only the entropy has to, only the limit of the entropy has to exist. The reason why this works is that this R has bounded size in an individual one, and therefore somehow not arbitrarily. So surprisingly, in quantum information, often the only relevant thing is the value of the entropy. This is why it works. So indeed, one would expect that I need to have some condition that the marginals match, but I don't need that here. I only need the condition that this converges.
But one example would be just take any family that you can grow that is not permutational invariant, just any translational invariant, and then randomly permute. Okay, so just take and permute it, and for every m, just take this permutational state, to make it bigger permutational state. This would be
Right.
permutational invariant by
Yes.
definition.
Yes.
Would be a family.
Yes, right.
Would,
Yes, you're saying any family of
Any family that
states
just-
can be made into a family of permutation. But that, of course, I know where the, let's say, question comes from, because if I do that, then there's no reason why this converges here, this limit that I have. So I need to actually assume that this, so the statement is if that converges, then this statement that this characterizes correctly the amount of information or how well I can compress is correct.
In some sense, you want to say there's a good thermodynamic limit of these
Yes,
things.
yes.
So that
But the thermodynamic
even if the
limit-
first two are wrong, it doesn't
Right.
matter.
But-
Most of them are going
Yes,
to be in
but-
the same phase.
But I don't even need that the limit, there's any other thing. So the different states, I think, like in the example of Ignacio, would be arbitrarily different. And the only thing I require is that they have the same thing. So they need to be similar only in that aspect. Maybe that's surprising, but generally, if you do information theory, you see that many properties, like how much randomness can you extract from a state, what's the compression, is only depending on an entropic property, and this is why this works. So at the end, the compression is actually given by, in a sense, one parameter thing. There's no other property of the state needed in the asymptotic regime. This is not obvious, but that's why I don't need to have this marginal, or that the marginals are identical. Okay, now if we look in, or sorry, 15 minutes. Yes, sure, I can now be fast. Now, how do we apply? Let me now discuss an application of this in the case that is hopefully interesting for people looking into problems like quantum information or the paradoxes, or I don't know whether they're still not called paradoxes, but puzzles, I would say. And the idea here is, or what I want to do is the following. So first of all, when I look into calculations that are done of the entropy of Hawking radiation, let's say the old calculation, old ones, the one by Hawking and so on, they use some methods, there are different methods to calculate the von Neumann entropy, and the methods are such that we just work with basically a scenario where we have one black hole. Now, the difference to these more recent calculations that were done is that they use the replica trick, where in a sense you create, at least intermediately in the calculation, just as a technical tool, many black holes and many Hawking or radiation systems, and somehow use that to calculate the entropy. And now one could hope, or what I and Jinsao Wang and my co-author were looking to is to ask ourselves, so if the calculation, even if it's only for a technical reason, introduces many copies of a black hole, could we somehow use these calculations to actually make statements, for example, about this regularized entropy that I just introduced before? Because that would give us a more operational statement about the question, or that would actually give us an answer. If you want to answer the question, can we compress Hawking radiation? We would need something like that, as I just argued. So first, of course, if I have a scenario where only one black hole exists and one big radiation system, I can anyway not match it to this scenario because we have here n copies. So I would need to go into a scenario, and I think this is the difference to what people are doing here, where I introduce many black holes not only as a technical tool to apply the replica trick, but I really think of a scenario where there are n black holes with n radiation systems, and the compression task is this one, where I have these n radiation systems that I compress together. So this is now the question, what can we say about that scenario? Now, if you look at the calculations that are done for the replica trick, let me just briefly write this down. So, of course, typically it's the idea that you look at these Renner entropies, H alpha, and just use the fact that in the limit where alpha goes to 1, we have the Renner entropies coincide with the von Neumann entropy. We can also, then the second step is usually to say, okay, it's hard to evaluate these entropies for small values of alpha, but let's just consider them for Renner entropies where the parameter is actually, okay, this is a different n. Well, I still use the small n, but it's now in a different context. So this is some natural number. And I evaluate it there and then make an analytic continuation for these alphas. So I calculate this. Okay, this has somehow the form. I got this correctly. Something like this. Rho. Then yeah, there's a formula like this. Now the replica trick uses the fact that I can evaluate this thing here by looking at n copies of the state and then use this swap operator tau, which somehow shifts n systems cyclic. Okay, that's let's say how I would describe this on the level of density operators. And I think the important point why one is even doing that is that this is something where I can now, so let's say from the quantum information perspective, I would say what you do by this is turning the calculation of an entropy into actually calculating the expectation value of an observable, which is a priori, by the way, something very suspicious because we know in quantum information entropy is not measurable. But indeed, what that is doing is to say, but we can maybe estimate it if you have many copies. And that's somehow what's going on. Now you could say what is done now is this is now turned into, so we now calculate this and say this is just the expectation value of an operator. So I can interpret this as an operator. And now I can use gravity tools like the gravitational path integral to calculate this. So now in order to calculate the expectation value of this is now in a setting where I have n copies of a system. Let's say this could be a radiation system R. So I just calculate this as a path integral with boundary conditions. I denote this just symbolically like this, where let's say if the boundary condition for one black hole was called P, I have now somehow an n-fold product of these boundary conditions, and that generates somehow n black holes, and then I evaluate this. Now, that's what is done technically in a sense. Now I will make this conceptual step and say, what if we interpret this scenario as the real physical scenario where we have many black holes? And I can even go further and say that what's going on here is I could in principle think of a scenario where I even produce many more black holes. Let's say capital N is now some much larger number. And I apply this swap, this tau operator on n of them. And on the remaining n minus n, I do nothing. I mean, I could also do this. That's of course gives precisely the same value. And however, I could write it here as I evaluate this on by generating capital N many black holes. Now, of course, somehow the outcome of these path integral calculations suggests that if I really look at the radiation, it's actually not in an IID state. Or you can also see it from a different perspective and say that if you start now, if you now want to go backwards. So now I somehow started from just technically calculating the von Neumann entropy. Let's now go the other way around and say what is actually calculated is this. And now ask what does this really mean in quantum information terms. Now the point is that if I have these boundary conditions of n black holes and I evaluate some operator, I have no guarantee that some intermediate state in this system is of IID form. That's now exactly an example where I have no physical reason to assume that if I generate n black holes, the state of the radiation is factorizes. And indeed, the calculations somehow suggest they don't. So therefore, I should doubt actually the whole replica trick, because the replica trick only worked because I actually assumed here it's ID. But let's now just go backwards and not make this assumption. So I go backwards and say that, okay, what I know is there's some state generated of R of n systems. It's maybe not IIT. I evaluate this expectation value. And now I want to understand what that means. Now, because these boundary conditions are symmetric on permutations, I could always assume that I again apply at some point later a random permutation. So I can argue that this state here is actually permutation symmetric. Now I can use Finetti to say, so here it's anyway irrelevant what the state is on all n systems, because the interesting operator only acts on the first n systems. I assume n is much smaller than n. So I can now say that this is the same as writing here only R1 until, okay, this is just I can basically go back the step I did before. So I just calculate this. Now now comes the quantum Finetti theorem, which tells me approximately this is a Finetti state. And of course, if it's a Finetti state, it has a very simple form, which I can easily understand. And I will now not do that, do this last part of the calculation. And what turns out to be the case is that this is the, now in the limit again, now I can answer this question, what are the limits? Now I have a procedure to define a family of states. So let's say I can put boundary conditions for an arbitrary n, and each of these n will generate a quantum state. So now I have a natural way to generate a family of states. And for this family of states, I'm now applying these theorems. Now I can say in the limit where n is very large, and at the same time, n, I can do both these limits. N divided by n goes to 0, and n becomes very large. What I'm getting is actually the regularized entropy. So that's what turns out to be the case. I didn't show now this last calculation, but that's just some standard analysis to get.
You also need a little n goes to infinity as well.
So yeah, so little n this n2 divided by n goes to 0 in a suitable way. Yes. So
wait,
yes,
but
so,
in your
yes,
definition of
yes, you're absolutely right. So this also goes to infinity under this constraint that this goes to 0. Yes. Right. And now you can see this is an example where
Why do you want n going to infinity?
Yeah.
Little n, I thought it was.
Yes, so this one is just a constant.
No, that's little n.
Why I want this to go in? Because I need that for the last step, because the regularized entropy has the little n, or has some, let's say, for the regularized entropy, I only look at that part. Remember, the regularized entropy was defined to be a limit for small n going.
I think that this step you might want to say that this is equal to the EW times H.
EW.
You had it for a definite state.
Yes,
Yeah.
right. I could say that, yes, here I could say this is now this something of that form. And I'm using that within the calculation to actually get here. So I didn't show this last step, but indeed, like I could say that this state is of that form. So a different, maybe what you were expecting is that I'm saying something like this is H of R even I can interpret this W as a random variable, and then I can write it like this. But this is the radiation conditioned on the W.
Yeah, I was expecting like the PW times H of sigma W.
Yes, and this is basically how this is
That's
defined,
fine.
yes. But it turns out this is equivalent also.
And that's this W would be what the we call alphas, the alpha parameters.
Yes, right, yes. So in a sense, one could say what this reproduces, this definition is on a very abstract information theoretical level, things that you cannot give meaning in, I think, when you talk about the alpha parameters from the gravity side.
But this is a very different limit for comparing the replicatrix for random entropy, because we want to take n goes to 1, but here you want to take it to infinity.
Yeah, so actually it's then, one can then show that now I can make these things more precise and show that even for n's, so I know the error of these. And actually, so the point is, or the problem is maybe I didn't now show the calculation from here to here. So what I'm doing in this calculation, that will probably answer the question, is I can, in the calculation, I fix the n's and let the large n go to infinity. And then I get all these like points I need for all n. And then I can analytically continue and get here. Now there's a separate step. So this n is somehow coming in again, like there are several steps going on by relating what I get again back to the regularized entropy.
Oh, okay.
So maybe I should have put more steps, but this is in, I will actually give the archive number of the paper if you want to read up on these steps. That shows this part, which I really didn't show, so it's not that this. So, so this calculation, particularly this last step, and also the answer to how are these n's and so on chosen, will can be found here. Now, let's say, let me conclude from here. So let's say the insight is now the following: that if we remember what does this do the recent calculations that are based on the replica trick tell us, then, for example, for the page curve, they, as you know, they reproduce the page curve. If here is the entropy, but what these considerations show that is that the page curve is actually calculated for the regularized entropy, which is precisely the right thing to give it an operational meaning. So in a sense, you could say the replica trick suggests one calculates the von Neumann entropy in an ID setting, but if we analyze this now with these Finetti tools, we find that replica trick calculates a different quantity, which is not the von Neumann entropy, which is a good thing, because in a non-ID setup, this is precisely the quantity that has the operational meaning of being a compression. So the conclusion is that this page really describes how well you can compress information or radiation in a setup where you really have n black holes, because otherwise you cannot apply this thing anyway, because you need repetitions. So these calculations are, in that sense, we're doing the right thing, but in an intermediate step, giving it, in a sense, the wrong name and say we did the von Neumann entropy. Now, if you compare to Hawking's original calculation, which has this ever-growing entropy, this is the von Neumann entropy, and now you see that from that viewpoint, you could say there's anyway no contradiction between Hawking's result and that, because the regularized entropy is generally much smaller than the von Neumann entropy. So in that sense, one could say, from this information theoretic viewpoint, that, let's say, this or the deviation between the two calculations can be explained by saying that one was actually calculating two different entropy measures, but that the operationally relevant one is that one. So if one asks how well can I compress information, the answer is clear from the quantum information perspective. Of course, provided all the assumptions that went into the calculations of these quantities are correct. So, okay, so from that, I think one can see that, I hope you got some, let's say, view that in quantum information, the thing we learned recently is IID is a dangerous assumption, but we can somehow deal with it. And one interesting, let's say, techniques are these Finetti theorems that have been developed in the area of quantum cryptography. Okay.